at UC Berkeley, then coming through University of Toronto briefly, and then for the past number of years, he's been at University of Southern California, USC, our neighbor to the north, and so we're happy to be able to have a more close connection with USC, with Daniel. And so just in terms of his research interests, Daniel's an expert in quantum information theory. He's written extensively about topics such as quantum error correction, quantum information, quantum control, and the subject of his seminar today will be the demonstration of algorithmic quantum speedup. So thank you for coming.
Okay, great. Well, it's really a pleasure to be here finally. We've tried to make this work for a while, and so it's really great to be here. And thanks for the invitation. You said I was in Toronto briefly. It was actually a brief 5 years, which were very, very snowy and cold. It seemed more like an eternity, actually. It was really nice to be in sunny Southern California. So what I'd like to tell you about is work that was done with another Vivek, also from Nepal, Vivek Pokharel, a graduate student of mine. And I have to say, I'm excited about this result. I think it's, in a way, at first, and I'll try to convince you of all that today. Okay, so the work is on a demonstration of an algorithmic quantum speedup, as we call it. It's in this archive paper. And to start, let's define what we mean by a quantum speedup. This is going to be very basic, but I want to make sure we get our terminology agreed upon. So a quantum speedup, for that we need a metric. And the metric that we like is time to solution. So imagine that you have a computational problem that you're trying to solve. And imagine that there's a way to verify the solution efficiently. And if that's not the case, then there are some complications, but we can deal with that. So we define the time to solution simply as the time it takes you to run a circuit. So that's in the numerator, the runtime. And because we're talking about probabilistic algorithms, we have to divide by the probability that we actually solve this problem. Right? If the probability is very small, then you're going to have to repeat your circuit many times. And so that's why it's in the denominator. So the time to solution is simply the runtime divided by the probability of solution. And so there are two parameters that enter, the problem size and the runtime of a circuit. Okay, so with that metric defined, I'd like to talk about what is a quantum speedup. And first of all, what is not a quantum speedup? So something like 100 times faster, that's not a quantum speedup. We're interested in scaling. It goes without saying. Okay. So we want a dependence on n, on the problem size. And we're looking for a quantum advantage in the time to solution that grows as a function of the problem size. And there are several scenarios like that. Most famous, of course, and the most desirable is an exponential speedup, such as what we suspect we get with Shor's algorithm, where the quantum TTS is polynomial in n, and the best classical is exponential in n. So that would be an exponential speedup. But we can also have polynomial speedups. And there are actually two types of polynomial speedups. The first is simply when the time to solution is a polynomial, and the quantum polynomial is smaller than the classical one. But also, we can have a polynomial speedup when we're comparing two exponentials. And this will be the scenario of interest to us here, actually. And so the quantum Q is less than the classical C. That's the case of Grover's algorithm, for example. If you take n to be the number of qubits. And so the classical time is 2 to the n, the quantum time is 2 to the n over 2 square root, and so you get a smaller q than c, just like here. Okay, so those are types of quantum speedups that are common in the analysis of algorithms. And now we can define a quantum speedup as the time to solution scales better with n for the quantum computer than the best possible classical algorithm. And there's a caveat here because what is best possible? In some cases, we have proofs, like in Grover's algorithm. In some cases, we don't, like in Shor's algorithm. In fact, in most cases, we don't have a proof, but we have various reasons to expect that the quantum algorithm is better than the best available classical algorithm. It will stay so forever. Shor's again being a case, quantum simulation being another case. But in general, in the best case scenario, we have proofs, and in reality, we just have the best currently available. Okay. All right, so with all that in mind, what is the status of quantum speedups currently to date? And I don't mean algorithmic proofs necessarily, or algorithmic results in hardware demonstrations, quantum speedups. So what do we know at this point? So first of all, I want to add another adjective here, which is unambiguous. And by unambiguous, I'm going to be referring to speedups where we don't have to rely on any assumptions whatsoever. Okay, that's the case that we're shooting for in this work, an unambiguous, assumption-free type of speedup. So do we have examples of unambiguous quantum speedups demonstrated on hardware so far? Assumption-free quantum speedups. And there are generally four main types of areas where we can hope to see examples of hardware quantum speedups. Quantum supremacy, quantum simulation, quantum optimization, and quantum machine learning. Those are the four leading areas. And what I'd like to claim is that at this point, there is no example of an unambiguous quantum speed that has been demonstrated, with one possible exception in quantum machine learning, and that is this very recent and very beautiful paper by Huang et al. On quantum advantage in learning from experiments. Yeah, we can talk about that. I think it's very close to meeting the burden of an unambiguous quantum speed proof, but isn't quite there yet. So despite all this beautiful progress, in particular, it started, I guess, with quantum supremacy with the Google result, but as I'm sure everybody here knows, that is definitely based upon a strong type of assumption, namely the non-collapse of the polynomial hierarchy. So that is not an example of an unambiguous quantum speedup. It is still a qualified or an ambiguous, if you like, quantum speedup. So this is what we're shooting for. We would like to have an unambiguous quantum speedup. And the context in which you can demonstrate such a result almost necessarily has to involve an oracular black box type setting, because that is the context in which we have solid, airtight proofs of a quantum speedup that cannot be beaten classically. So that's the context for this work. And in order to explain what we did, we have to go back to 30 years of quantum computing prehistory. Bernstein-Vazirani, one of the very first algorithms that was proven to exhibit a quantum speedup. By the way, if anybody has a photo of Ethan Bernstein, I'd love to have it. I couldn't find it. And so just to remind you, the Bernstein-Vazirani problem, you can interpret it as a game, as a bitstring guessing game. So suppose you have a secret bitstring B with n bits, and your goal is to guess that secret bitstring. Now, there are certain rules to the game, and the rules are there is an oracle, and this oracle, you give it a guess, X, and it returns, it knows B, but it doesn't tell you B, of course. It tells you B dot X mod 2. Okay, so the bitwise inner product mod 2 for whatever your guess was. That's what you get back, which is 1 bit. Okay, so you get back 1 bit. And in the original Bernstein-Vazirani setting, the bit string B was fixed. So you keep on guessing. And we're going to modify that. In our version, for reasons that will become clear in a second, we change the bit string, the secret string, every time after you make your guess. So the oracle, you send her X, and she tells you B dot X, and then she picks a new bit string B. Okay, so that's why we call it single shot, Bernstein-Vazirani. Now the goal is still for you to guess the secret string B. And so what you're going to do is you guess, after you get B dot X mod 2 back, you guess the entire bit string B. And you win if you guessed it, you lose otherwise. And like I said, a new string is selected and the game starts over. So what's going to happen here, classically? Suppose, without loss of generality, that your guess is the 1, then all zeros bit string. Well, the inner product mod 2, in that case, is just the first bit, B1, right? So you learn 1 bit. And it's very easy to convince yourself that no matter what you try, you will never learn more than 1 bit. So the best possible classical strategy still yields just 1 bit. That means n minus 1 unknown bits remain, and therefore the probability that you will correctly guess the entire bit string B is 1 over 2 to the n minus 1, because you learned 1 bit. Okay, so that's your probability of guessing after 1 round of playing the game. So you keep playing the game, and every time this is your probability. So what is the time to solution for the classical player? Well, the time to solution, remember, is the time to run a circuit. And in this case, the time to run the circuit, the oracle still has to compute B dot X. Okay, and that in general can take n steps. In fact, I'll show you in a second the circuit that does that. You'll see that takes time n for the oracle to execute the calculation, divided by the probability that you correctly guess the string. So the classical time to solution is n times 2 to the n minus 1. And what this means is it's trivial. It just means that it's going to take you that much time in order to finally get lucky, on average, and correctly guess the hidden string. Again, the string changes every time. Right? So on average, you're going to play this many rounds, an exponential number of rounds, before you find the correct string. So here is I'm going to be very pedantic about this because I'd like to explain the quantum version of this as well. Here is the classical oracle that computes P dot X mod 2 for the particular hidden string all ones. Okay, if the hidden string is all ones, what you do is you just do XORs or C naughts in quantum language from every bit, every one of the n bits to an ancilla, and you compute the XOR, you add them all up, and in this case, you will get the 1111.x, and that's what the oracle is going to return. Okay, so this is the classical reversible circuit, and you see it takes time n for the oracle to compute this function, b dot x. Right? What if there was a different bit string? Let's say the hidden string was 0 and then all ones. Well, then you drop the first XOR. Okay, and in general, it's easy to convince yourself that the rule for constructing the circuit is you just look at the bits in the secret string D, and wherever there is a 1 in position number I, you put a C naught there or an XOR between that ith bit and ancilla, and otherwise do nothing, just like here. Okay, so there are at most n C naughts, and therefore running the oracle takes time at most n. This is the classical circuit, and the quantum circuit, which we all learned at some point, is just the addition of Hadamard's before and after the classical oracle, and then reading out in the computational basis. So the ideal quantum single-shot probability, miraculously with the Bernstein-Vazirani algorithm, which is this circuit, is 1. Right? That's what you can prove in a couple lines. And therefore, because ideally, in the noiseless case, this circuit succeeds with probability 1 in returning the correct bit string, the time to solution is the time it takes to run the circuit, which is as n, and actually n plus 2 if you don't do count measurements, n plus 3, but it's basically n. And you need NC naughts, just like in the classical case, divided by the probability of success, which is 1. So the quantum time to solution is n. Okay, and that's it. And I should say that in the standard Bernstein-Vazirani problem, which is not single shot, right? The original version from 30 plus from 1993. As I said before, the secret string is fixed. So classically, the problem is solved in just n oracle queries because every time you get another bit, right? And it takes time n to compute the oracle. So the classical time to solution in the original setting was n squared compared to n quantumly. And so the original speedup was just linear, n squared versus n. But in our modified setting, where the bit string changes every time, it becomes exponential classically, but it remains n quantum. Okay. So we formulated a problem for which provably there's a quantum exponential advantage in this oracular setting. Okay, and just like in the classical case, if you want to construct a different oracle for a different secret string, it's exactly the same procedure. For example, for the 0, 1, 1, you just drop that first sign. Okay, so that's the context of the problem. And let's just now try to quantify the speedup story. So if there's no noise, for an ideal quantum circuit, I just hopefully convince you that the classical time to solution is n times 2 to the n minus 1. The quantum time to solution is n. So the speedup ratio is 2 to the n minus 1 in the noiseless case. Right? That's an exponential quantum advantage. Okay, but now, what if there is noise? Which, of course, is the context of interest to us. So with noise, every gate, measurement, so on is imperfect. And in the most naive model of quantum noise, the probability of succeeding is no longer 1 for the quantum circuit. It is going to be exponentially decreasing in n, right? Because for every additional C naught, other gate that you have to invoke, let's just assume that the fidelity is multiplied. So you expect that the quantum success probability is not going to be 1, it's going to be 2 to the minus lambda n, positive lambda, for some lambda which characterizes all the noise in the circuit. It's an extremely naive model, of course, but it will do for our purposes. So, in fact, the expected time to solution ratio or speedup ratio is going to be this. The numerator hasn't changed, but the denominator is now this time n to compute the single circuit times this 2 to the minus lambda n, which is the probability of succeeding in a noisy circuit. So the actual expected speedup ratio is 2 to the 1 minus lambda n, where we then get a quantum polynomial speedup, provided that lambda is less than 1. Right? That's the summary of our theoretical expectations from this setup. Is this clear so far? Any questions?
Sorry, why is it polynomial? It's still 2 to the...
Okay, so let me go back to my introductory slide. I think you walked in a second after I explained this. So I was talking about types of speedup. So it's this third bullet here. We're comparing 2 exponentials with 2 different exponents. Okay, just like in Grover. Okay, so what we should expect in a noisy in quantum circuit implementation of a single shot Bernstein-Vazirani problem is this type of scaling. And we are going to get a quantum advantage, a quantum speedup, polynomial speedup, provided that lambda, this noise parameter, is less than 1. Okay, so that's the key thing to keep in mind. Is lambda less than 1 or not? All right, so with this out of the way, there might have been another question.
Just a very small comment. I think in the denominator, you need a 2 to the plus lambda n.
Well, it's the probability, right?
But the time to completion should be 1 over the probability.
Oh yeah, you're right. That is absolutely right. Thank you. Okay, we'll fix that. Anything else? Questions? Okay, good. All right, so let's go ahead and try this on the IBM Quantum processing units. And we were fortunate enough to, for a while, have access to the paywalled quantum machines. And we decided to pick 2 of them, Montreal and Cairo. These are 27-qubit machines. This is the heavy hex layout that IBM has been using. You can see the qubits. You can see how they're connected to readout resonators, how they're multiplexed. This has some relevance for some of the noise that I'll talk about later. And IBM provides a lot of data, which they update all the time. So here's a snapshot of what we found out about Montreal and Cairo when we ran these experiments. And of the many numbers here, the only ones I want to emphasize are the 2-qubit gate error. And for Montreal, you see that 2-qubit gate error is about a factor of 3 lower than it is for Cairo. So we expect Montreal to be the somewhat better machine. In fact, if you compare all the other numbers, they're very similar, but they do differ here. But at the same time, the readout on Montreal, the readout duration on Montreal is substantially longer than on Cairo. So you expect Montreal to have overall higher fidelity, but to be a slower machine as a consequence. And also in terms of quantum volume, this agrees with the expectation Montreal is a little better than Cairo. All right, so now we just ran this single shot Bernstein-Vazirani problem on these 2 machines, and I'm going to show you the one result here for Cairo for the 6-bit version. So with 6-bit, there are 64 possible secret strings, and we tried all of them. Right? And so here is the oracle number, or if you like, the secret string number, versus the actual detected state. Ideally, we would expect the algorithm to succeed with probability 1, and there would only be points on the diagonal here. So for every secret string, you would exactly find that secret string at the output. But in reality, there's noise, of course. By the way, the strings here are sorted by increasing Hamming weight. Okay, so you see that there's clear progression from dark to orange, which means a decreasing probability. And that makes sense. This is the direction of increasing Hamming weight. And we would expect that when there are more C-naughts in the circuit, there will be more noise. Right? And so higher the Hamming weight, the more C-naughts you have in the circuit. And so that agrees with our expectations. So deeper circuits, in other words, have more decoherence. Okay, but let's quantify what's happening here. And if you average the success probability, the success probability is something that you can compute for a given oracle or a given secret string. But if you average over all of them, all 64, you find that the quantum success probability here is already actually very high, 72%. It's not 100%, but classically, you would expect a success probability of only 2 to the minus 5. 6 bits, you learn 1 every time, and that's only 3%. So a massive quantum advantage, it appears. But the real question is whether that is sufficient for quantum speedup. And for that, it's not sufficient to just look at the probabilities. As I was emphasizing, we're interested in scaling with n. And this is just a single value of n. And what happens if we look at the time to solution metric. And now we are plotting time to solution as a function of n. So this is log time to solution as a function of a problem size. And crowded plots, I'll try to walk you through it. First thing is just these white grid lines in the background, if you see them. That is the classical scale, the n times, now I got the exponent correct, it's n times 2 to the n minus 1, okay? So that's what we want to beat in terms of slope. And these dashed, almost horizontal lines are the ideal quantum scaling if we had a noiseless quantum computer. Different for Montreal and for Cairo, because remember Montreal is the slower machine, so we actually plugged in the real numbers here, so this is the expectation for the time to solution. If Montreal were an ideal machine with that readout that is provided by IBM. And now finally, and most importantly, here's the data. So the data is Montreal and Cairo for problem sizes going from 1 all the way to, well, you see where these curves terminate. And the thing to take home from this is that when we extract the slope, lambda, by fitting to the last bunch of data points, there's some finite size effect here for small n, but then it really starts to look exponential. It's very clear that we have a quantum slowdown. The slope is worse than classical. Lambda is greater than 1. Lambda is these numbers here. So that's bad. And in fact, it's even worse than that. We have what I like to call a quantum blowup, because there's a reason these curves terminate. In fact, on Montreal, we never found a correct solution after 10,000 shots for n greater than 60. So for n 17 on Montreal and for n 21 on in Cairo, the solution is just never found within 10,000 shots. That doesn't mean that it's actually probability is 0. Of course, you keep trying, but effectively, the time to solution becomes infinite. Okay, so this is not great, but also not at all unexpected, because we haven't done any kind of error correction or error suppression so far. And these clearly are noisy machines. Nevertheless, it's kind of disappointing. And also, by the way, word of caution here, if you were to stop at, let's say, n equals 10, you might fool yourself into believing that you have a quantum speedup. If we stop the experiment at n equals 10 and try to fit the slopes from there, hey, quantum speedup. No, but that's not the case. So we went as far as we could with these machines, up to the largest problem sizes. Okay, so what do we do? Of course, quantum error correction comes to mind, but we don't have a lot of qubits. And so we have to resort to more economical means. And dynamical decoupling is a well-established alternative, the poor man's alternative. And so just to remind you, what is dynamical decoupling? It's an open-loop type quantum control technique where you try to suppress the interaction between the system and the bath. The way you do it is by essentially exploiting the ability to apply gates. We call them pulses in dynamical decoupling. And the most general dynamical decoupling scheme will have some pulses of different types. So think of this as different gates, if you like, that are applied at different intervals. And in between, there's free evolution. So F stands for free evolution. A trivial example of how dynamical decoupling works is if you can find a pulse, P, that implements time reversal. So in particular, it has the property that P, H system bath, Hamiltonian, P dagger, puts a minus sign on Hamiltonian. If that's the case, and here is a very short calculation to convince you that you essentially cancel the system bath interaction in the following way. Suppose you have a free evolution, followed by a pulse, free evolution, pulse. Right, now you can lift the P and the P dagger into the exponential. By assumption, this negates the sign. So this minus here becomes a plus. And then the forward free evolution gets canceled with this time reverse free evolution thanks to the pulse. And overall, you have the identity operation. So this is the basic idea of dynamical decoupling. You time reverse the evolution subject to the system math interaction. And a specific example of that is if you have pure dephasing. If you have this type of system math interaction with the Z, and if you apply X pulses, because X anticommutes with Z, you get the minus sign, and you have time reverse this system math interaction. Okay, so I have to say this is all just the first order in time-dependent perturbation theory, and that's very important. There will be all sorts of corrections that appear to higher order, but staying with this first order time-dependent perturbation theory, it's easy to show that you can actually cancel any arbitrary system math interaction. Any arbitrary system math interaction can be canceled using dynamical decoupling with sufficiently many pulses. For example, for a single qubit, the most general system math interaction can always be decomposed in this way. And there's a well-known sequence known as XY4, which is the sequence. You can easily convince yourself that if you apply XY, XY interspersed by free evolutions, that multiplies to identity. For this most general single qubit system math interaction. Okay, so think of it as stroboscopically canceling the system math interaction. At the end of every round of 4 pulses like this, for an instant, the system math interaction is canceled, at least the first order. Okay, and this is very generalized to many qubits, multi-qubit system math interactions, and not just qubits, and so on and so on. And it's also possible to generalize it well beyond first order perturbation theory, and actually generalize it to nth order perturbation theory with appropriate pulse sequences. So already back in 2018, we tried these kind of tricks on the IBM machines that were available at the time. So this is from this paper from 2018, also with Vivek Pokharel and 2 other guys. This was on at the time, they had a 16 qubit device. And this is the fidelity as a function of time. For the unprotected case, the no dynamical decoupling curve is the black curve here. You see how the fidelity drops precipitously. And what I mean by fidelity here is this is averaging over 36 different initial states. We're just trying to preserve these states. So 30 random initial states plus the 6 Pauli eigenstates. Okay. So the average over those 36, fidelity decays very rapidly, but with dynamical decoupling, the XY4 sequence in particular that I just mentioned, you see that the decay is slowed down significantly, at least for short times. At the time, we didn't really understand why there was this oscillation here, and now we understand this crosstalk. So what dynamical decoupling does, among other things, is it removes qubit-qubit crosstalk, particularly ZZ type crosstalk, which is very desirable in superconducting qubits. We tried the same on Rigetti, and at the time, Rigetti had this 19 qubit chip, and it's a similar story. The blue curve is without dynamical decoupling, and the yellow curve is with dynamical decoupling. You see how fidelity decay is slowed down. Okay, so now XY4 is by no means the best sequence out there. There's a huge zoo of dynamical decoupling sequences. This is an old field that started in the 1950s in NMR, and quantum information people have contributed greatly to further developing it. And we now know that there are pulse sequences that are robust to pulse imperfections. That's a very important aspect, because our gates are imperfect. And we also know how to cancel system math interactions to arbitrary order, as I said. So there's another paper where we tried that on the IBM GPUs. And one of the best sequences that we found in the survey that we conducted in this paper is the so-called universally robust sequences that were discovered by Genov et al. I won't go into too much detail about how these universally robust sequences are constructed, but basically the important thing about them is that the word robust refers to robustness to imperfections in the pulses. The pulse is actually, it's a gate. It takes a finite amount of time. While the gate is on, while the pulse is on, there's decoherence happening. You have over-rotation, under-rotation errors. You have axis angle errors, and so on. So it turns out that the sequence by Genov et al. Achieves order n over 2 cancellation of pulse errors using just n equally spaced time pulses. I'll illustrate that in a second. But here's an example of the UR6 sequence. So this is a sequence that cancels errors in the pulse itself to third order using a sequence of 6 pulses. You apply a pulse with angle 0 with respect to the x-axis, and then 2 pi over 3, and then 0, 0, 2 pi over 3 again, and then 0. That turns out that is the sequence that cancels errors to third order. And here's a result from this reference number 1 here, showing what happens if you try to preserve the minus I state on the IBM machines using 3 different sequences compared to free evolution. And you see that if you use the XY4 sequence, this is fidelity versus time. I should start with the free evolution without doing any dynamical decoupling. You see the fidelity decaying plus these crosstalk oscillations. XY4 doesn't really help you very much. CPMG, which is the famous NMR sequence, doesn't help you very much. But the UR20 sequence does a marvelous job of preserving fidelity and removing crosstalk. And just to give you a little bit of intuition about what this looks like, so here's a comparison between x/4 and UR6. And let's say the goal is to preserve the plus state, but our pulses had 15 degrees over rotation and 5 degrees axis angle errors. Okay, so instead of rotating by pi, we rotate by pi equals 15 degrees, and instead of the axis being x, it's x with a 5-degree error. If you try the XY4 sequence, you try to preserve a state to here, you actually, with these errors on the pulse, you end up there. So a big error. If you do the same with the UR6 sequence, it does a more complicated trajectory on the Bloch sphere, and it ends up almost exactly where it's supposed to. Okay, and that's UR6. So that's what is meant by a robust sequence. Despite there being errors in the pulse, it works extremely well. Okay, so we did a survey for our Bernstein-Vazirani problem on both Montreal and Cairo. And we found empirically that the UR14 and UR18 sequences were the top sequences on these 2 machines. We did that for the n equals 10 bit problem. And then we just ran with those sequences. Okay, so all this is the story of how we're going to deal with the problem of imperfections, decoherence in these circuits, which killed the quantum speed. So what happens when we use this dynamical decoupling method? That's what I want to talk about next. But first, let me just tell you how we insert the dynamical decoupling sequences into our circuit. You might wonder, how do we do that? Well, so here's the abstract circuit. Here's what it looks like from Qiskit. And the thing to notice is that there are these gaps. You can also see them in the ideal circuit. And so there's a long gap here. This qubit number 1 here is just sitting there idle, being bombarded by decoherence and decaying away. So we take advantage of those gaps, and wherever there's a gap, we fill it with a dynamical decoupling sequence. And sometimes there are 2 gaps, like for qubit 1 here. And so we fill those in. I'm showing schematically 4 pulses here, but actually, like I said, it was the UR14. That's a 14 pulse sequence, or 18. So we fill those gaps with those pulse sequences. And that's it. That's really all we're doing. There's no fancy quantum error correction here. There's no encoding, decoding circuit. There's no syndrome extraction, none of that. We're just using the existing pulses or gates that are already part of the arsenal to perform these dynamical decoupling operations. That's really all there is to it. So we're just adding more gates. And you might say, well, wait a minute, if you're adding more gates and the gates are noisy, you're just adding more noise. But this is done in this theory-based way where we know that these additional gates that we're adding are supposed to have a desirable effect. And do they? Okay, that's the question. So here is on the left is what I already showed you. This is the SSBV6 without dynamical decoupling on the left. And here is the result when we add dynamical decoupling. And you see that all this low probability results that we were getting for the high Hamming weight strings, those are now much better. Okay. In fact, the average success probability went up to 80%. Okay, so is that good enough? This is just one data point, right? This is just an n=6 result. Is it sufficient to get a quantum speedup? And
can I ask a question? What's interesting to me is that you have all these sort of spurious results in the lower left and the upper right. And it seems like with the DD pulses, you still have some lower left stuff, but almost all the upper right stuff gets almost erased. Do you have an understanding of why that is?
Not really, but let's see. Maybe we can figure this out in real time. So a point in the upper right means that your input was a low Hamming weight string, and your output was a high Hamming weight string. Yeah, okay, so I guess that makes sense, right? So all these machines have a tendency to spontaneously emit. And so they prefer to go to low weight, low Hamming weight, right? Lots of zeros. So that's why you're getting, whatever you're doing, you're getting low Hamming weight strings. Okay.
So it's all spontaneous emission, T1.
Well, not all of it, but that I think explains both the tendency here for there to be more errors on high Hamming weight strings and also what you observed, which I hadn't even really noticed until then. Okay, but we're interested in scaling and speed up. So here again is the result from before, right, where we had not just a quantum slowdown, but even a quantum blowup. This was without dynamical decoupling. And here's what happens when we do dynamical decoupling. And so it's these UR14 and 18 sequences that I mentioned to you. And you see very clearly how the slope, Montreal is brown and Cairo is blue. You see how the Montreal slope has decreased significantly. The Cairo slope has also decreased, maybe not as significantly. And when we fit these curves from the end, as you see here, the new lambda values are much improved. So in particular, the Montreal exponent is now 0.6, plus or minus 0.03, and this is 2 standard deviations. So we have 95% confidence. Unfortunately for Cairo, the result is not as good, right? It went down from 1.28 to 0.98, but plus minus 0.2, so we can't really definitively say that lambda is less than 1 here. But for Montreal, we have high confidence that this is a quantum speedup. And by the way, if you're wondering why the Cairo result terminates here at n=23, and that is not a quantum blow-up result again. That is just because it turns out that there was a problem with one of the resonators, the readout resonators, and because they're connected, the qubits are connected to the same readout resonator, we actually had to remove from our analysis 3 of the qubits. So we actually treated Cairo not as a 27 qubit machine, but rather as a 24 qubit machine. 1 qubit is an ancilla, so 23 is as high as we could go on the Cairo. Anyway, that's a minor point. Really, the important point is that we now have this unambiguous quantum speedup. For Montreal, you see the slope less than the classical slope. So this is a scaling advantage in the time to solution. That's the gold standard. It's unambiguous because I define unambiguous as the case where we have a proof that the quantum algorithm is better than the classical algorithm, and the best possible, not just the best available, the best possible classical algorithm. And of course, you can wonder whether this is this continues, and what if we had a higher number of qubits on a different machine and so on. Well, we don't have. I'll get to this. We don't really have results for more qubits. We got as far as we could with these machines. But what we can do is we can analyze how robust this result is in some sense, and we do that by computing the slopes up to some maximal size. So what I mean by that is, imagine that instead of going all the way up to the end here, let's fit the slope to, let's say, n equals 14, up to n equals 14. So up to n equals 15, 16, and so on. If we do that, this is now the slope as a function of n, where we just compute the slope up to this value of n. Okay? So instead of fitting the slope all the way up to n equals 26. And without dynamical decoupling, you see how the slopes up to a certain point, in other words, this is like n equals 14 is like treating these machines as if they have only 14 keys. You see that the slope is initially less than 1, but then without dynamical decoupling, it climbs into the danger zone here of being greater than 1. So you might fool yourself into believing that you have a speed up for a small number of qubits, but then if you continue, it's clear that you lose the speed up. With dynamical decoupling, on Cairo, the slope is initially low, but then it starts to climb, right? And it gets right into the red zone at the largest possible number of qubits. On Montreal, we see no evidence of the slope doing anything dangerous. So it's tempting to extrapolate from here. And of course, it is mere speculation. Who knows? Maybe if you add one more qubit, the world ends and it just blows up. But if we just extrapolate, then we can probably keep going for a while and claim a quantum speed up here. Okay. So that's the story. Now, naturally, we want to continue this and extrapolate to larger problem sizes. We use the Falcon process technology, which dates back to 2019 with 27 qubits. There are 3 such machines, maybe there are more in fact, and we use 2 of those. We also were interested in what happens with the later generation machines. Hummingbird has 65 qubits, and the Eagle generation is 127 qubits. But unfortunately, those jobs never finished as of me recording this. So I don't have results to show you for these larger machines. I wish I did. We're also working with Rigetti, and they have now released an 80-qubit QPU, an Aspen M, and we're working with them on testing these types of algorithms in dynamical decoupling sequences, and that's also work in progress. So to conclude, we defined this problem, a single-shot Bernstein-Vazirani, that has a provable quantum speedup, free of any conjectures. It's unambiguous. It's obviously implementable on current quantum hardware. We have an unambiguous quantum speedup demonstration. This speedup is possible with dynamical decoupling, but apparently not without it, at least in terms of the experiments we conducted. Without dynamical decoupling, we see a quantum slowdown. With dynamical decoupling on one of the 2 machines, we see the speed up. And what we'd like to do going forward is, like I said, attempt larger problem sizes. Dynamical decoupling is very rich. There are many opportunities for further optimization. By no means have we found or implemented the best possible sequences. So it's a really interesting area to try to get better results. And in particular, I'm pretty sure that we can extract a quantum speedup out of Cairo if we use a better DD sequence and reduce decoherence and pulse errors even more. And finally, of course, there are other algorithms that are tempting in this context. So we're now working on Simon's algorithm, and there are some encouraging results there already, which are not quite ready for prime time, but we are seeing similar things for Simon's. Okay, and that's it. I want to thank you and Vivek, especially Vivek Cocorel, who did all the hard work. Thanks.
Okay, questions? I'll start with Vivek.
Okay. So one question came to my mind because you talked about the Google quantum supremacy paper, right?
Mm-hmm.
So is there a connection like with quantum speedup imply quantum supremacy in a way, or like do we need to hear something more?
Quantum speedup is definitely an example of quantum supremacy. So yes, I would say quantum speedup implies quantum supremacy. The other way around, as quantum supremacy imply quantum speedup is what I'm putting a question mark on, because again, it depends to some extent on how you define quantum speedup, an ambiguous versus an unambiguous quantum speedup. Do you need to rely on additional assumptions? Quantum supremacy, as it is defined currently, is a speedup relative to the assumption that the polynomial hierarchy doesn't collapse, which is a very, very good assumption. Okay, I mean, very few people believe that P equals NP. You actually need something weaker in quantum supremacy. But nevertheless, it is an assumption. Same with Shor. So if somebody tomorrow demonstrated an experimental version of Shor's algorithm with a speedup, the time to solution type speedup for factoring, it would still not be an unambiguous quantum speedup, because who knows, that could be an efficient classical factoring algorithm.
I have one more a bit related to the crosstalk, because there was an IBM paper where they said, like, if you have two qubits and you drive the two qubits by a phase, then you can remove the crosstalk between the two qubits by suitably tuning the phase factor, right?
Mm-hmm.
Is it the same mechanism that works here when you have this dynamical decoupling, reducing the ZZ crosstalk that you said?
So I'm not sufficiently familiar with the result you're referring to, but I can tell you how it works here, and maybe you can tell me if it's the same thing.
Okay.
So when you have ZZ crosstalk, what you do with dynamical decoupling is, suppose you apply an X pulse to one of those two qubits.
Okay.
Okay, so now X identity anti-commutes with ZZ, right? So you're putting a minus sign in the sense that I described, you're time reversing a ZZ interaction. So essentially with dynamical decoupling, you are making that interaction go forward and then backward in time, and it gets canceled. So that's the dynamical decoupling mechanism.
So it's a bit different mechanism, I guess.
You're symmetrizing. That's the really proper way to say it is. Dynamical decoupling is a type of, more generally speaking, it's you're symmetrizing over a certain group, which is the group generated by the dynamical decoupling pulses. You're computing the group average.
It's the same mechanism that cancels the SSB would cancel the GT as well, right?
Yes, that's right.
Other questions? Matt Leaker?
Yeah, so it's a very nice work, by the way, but I want to push on this unambiguous quantum speedup issue, because, traditionally, these computer science people have not regarded query complexity speedups as like gold standard, and there's a reason for that, which is that you have to say, when you have the oracle, you have to say, okay, what's the classical equivalent of this oracle? Right? What's the one-to-one comparison between this oracle, one use of this oracle, and one use of that oracle? Now, so with the standard oracle model, of course, you get provable model because you get speed up, but there are other sort of models of the classical oracle that you could, the classical equivalent of the quantum oracle that you could adopt, which would give you different results. So, for example, if you, I don't know if you're familiar with this work of, like a Larson, where he uses like a Speck's toy theory type of classical oracle, and there you lose many of the oracle-based speedups or even complexity speedups.
Yes, I think that's a very valid point. So there's a lot of danger in oracular speedups. You can even prove that P equals NP relative to a certain oracle. So what we're doing here is we are comparing apples to apples. Right? So the classical oracle is the exact same oracle as the quantum oracle. That's the story here.
Well, I mean, it isn't because the quantum oracle has Hadamard's.
Oh no, that's not part of the oracle, right? So
Okay, but if we adopt a kind of classical system that can have an element of Hadamard, like in the Speck's toy theory, then you can have exactly that, pretty much.
well, okay. I mean, if you have a classical theory where you can operate coherently on superpositions, that's starting to smell a lot like a quantum theory.
Well,
So what is this classical theory?
well, it's just a theory in which, well, okay, I'm not going to take too long to go into the details here, but if you look at these papers that like Larson has written, I don't know if they do Bernstein-Vazirani, but he definitely looks at the Deutsch-Josephs-Simon's algorithm in particular in that context.
Yeah.
I mean, it's controversial, okay, because it's a question of what do you consider the classical equivalent of a qubit, what do you consider the classical equivalent of
Right.
an oracle, and what's the fair comparison? And I wouldn't say that there's a unique answer to that question.
Yeah, so typically the kind of critique that I hear regarding the oracle story is of a different nature. So I might as well bring that up as well. And it's more a pedestrian version, I guess, of the objection, which is, I mean, look, if you hide the information the oracle has, sure, then you get speed up. But as soon as somebody's allowed to look inside this black box, well, I mean, you can immediately guess what the hidden string is, right? But if you know the rule, this rule, the rule for the sequence, it tells you exactly what the hidden string is. Right?
Yeah.
So this is, to me, this is a powerful critique. That is certainly not true of Shor's algorithm. You can look in the quantum circuit if you like. You're not going to guess the factors by looking at the circuit. Or random circuits used for supremacy, again, no way of guessing what the output distribution is going to be just by looking at the circuit. So I think that is a powerful critique of any oracular type of speedup. But that's why I think the right way to interpret this result is as a quantum versus as a game, where you have a quantum player and a plasma player. And the quantum player wins, according to the rules of this game. Right? This would be great for a TV show. So that's the context, and that is not an uninteresting context, because there are various cryptographic scenarios you can imagine where somebody has access to the black box and you just don't. Sorry, but it's locked up and it is literally a black box. You don't have the key. So that's the context. And yes, one can argue about different caveats. So that's the caveat here. You are not allowed to look in the box, and it's a fairly artificial restriction. On the other hand, with other quantum speedups, we don't have proofs. So that's another caveat. So, and your objection is actually very interesting. I hadn't thought about this version of classical computing that is close to quantum computing in some sense. So I'd like to understand better what this model is. Yeah.
Sagar, I think you got a question.
Yeah. So Manu was showing this TTS versus N plots. So before dynamical decoupling, so there was this speed up at the beginning, but then there's like a quantum slowdown. Yeah. So this could stem from my misunderstanding of unambiguous terminology. So when you have the dynamical decoupling, you're still stopping at some n, right? So how do you know before claiming unambiguous algorithmic speed up that it won't behave differently for larger n's?
Yeah, so we go up to the largest end that we can. Right? And that's going to be true for any machine anybody's ever going to build. It's going to have some finite number of qubits in it. Well, maybe that's not true for the photonic machines. I guess that's a little murkier there. But certainly any superconducting quantum device will have some finite number of qubits. And so you're going to check your scaling up to the largest possible number that's going to fit. And then you have to stop. And then you have to wait until next year somebody adds a few more qubits. So that is the nature of doing empirical scaling analysis. What I tried to convey with this story here, right? And this is the slope. This is the full story of the slope. The slope up to n. Every point here is the slope up to that value of n. And so, as I was saying, I think if you look at this slope, the one for Montreal with dynamical decoupling, you see that it's very deep into the green zone and doesn't protrude into the red zone. And so, you can extrapolate. Extrapolation is up to you. I'm not going to provide a warranty here, but I'd put my money on this extending by a few more qubits.
So when you do these experiments and you limit it up to less than the number of total qubits there are, how do you pick these qubits?
Yeah. So, okay, there are lots of details that I didn't talk about here, and that is a very important detail that you just asked about. You have to pick those qubit wisely, as it turns out, because there are some good qubits and bad qubits, and so we tried for every value of n, we picked the best qubits. Okay, so we tried to make some kind of a chain that had involved only the best possible qubits. If you see some irregularities here, like the slope going a little bit up and down and so on, that probably is because, like right here at n equals 13, we probably were forced to invoke a qubit that was not as good as the qubits that we had when we only went up to n equals 10. But the rule of thumb was always pick the best qubits.
Okay, I think we're out of time. Maybe if there's any burning question on the Zoom participants, I'd like to ask a quick question.
Well, I have a quick question. Just a second.
Go ahead.
It's a follow-up question, probably to the one of Andrew. Can we go just a second back to the success probabilities, where we have with and without dynamical coupling? So what I was curious is also, besides the fact that they tend to have more hits more wrong results at the bottom rather than the top of the diagonal, how come the distribution is also very similar in the two cases? So you see clusters that they are very, very similar, even though fainter in the two cases. Just was curious about that.
Yeah. I don't know, to be honest. I suspect that it's similar to the answer that I just gave about the role of good and bad qubits. But no, I don't know. We could look into that.
Okay, thank you.
Well, I think you're also right. If there's T1 processes, if it's spontaneous decay, then that's not, your DD pulses won't help those, right? So,
Oh, they do. Yeah, DD, I mean, so again, look at the the most general system bath Hamiltonian on a qubit absolutely includes those processes as well, right? This is the most general thing. So T1 is energy relaxation, so that involves, let's say, sigma x in this Hamiltonian. And you can absolutely cancel sigma x. Though maybe what you're getting at is Markovian versus non-Markovian. What you're not going to deal with is Markovian errors.
Yeah. All right, we're out of time, but just so you know, so we will be taking Daniel's lunch at noon at the faculty club. So if you want to join us there, you're welcome to do that. And let's thank him again for his nice talk.
Thank you.